Finishing up our study of logarithms, we want to take a look at some different exponential and logarithmic models. We're going to look at how to apply exponential growth functions, and an exponential growth function is nothing more than an increasing exponential function. We'll look at exponential decay, which is represented by a decreasing exponential function. Another exponential function that you may not be familiar with is called a Gaussian function. You have a Gaussian function when you combine an exponential function, e to this power, along with a quadratic function. You see this factor is squared, and that's where we get the quadratic function from. So this function looks exponential until we get to the y-axis, and then notice that it's symmetric across the y-axis and turns and becomes a decreasing exponential function on the other side. We would say that a Gaussian model looks like a bell curve. And if you take statistics, next year you'll learn a little bit more about the bell curve. We also have something called the logistic growth model. Notice here that the exponential function is in the denominator. So we have an increasing exponential function, and then it begins to even out. And this logistic growth model follows a horizontal asymptote at the maximum and at the minimum of the function. And then lastly, we'll look at logarithmic growth models. It's just the graph of a logarithmic function, and see how that applies to real-world applications. So our first goal is to model exponential growth and exponential decay. So the mathematical model for exponential growth is modeled by f of t, a function of time, is equal to a sub 0. Remember, we discussed a sub 0, and we said that a sub 0 is our initial amount. In our exponential growth model, we have the initial times e to the k times t power. Or a, our balance, equals a sub 0 times e to the kt power. So notice that f of t is a function of time. A is also a function of time. We compare this to, we have our initial amount compared to our current amount. Let's define the variables a little further. You notice that we have k in both exponents. So if k is greater than 0, the function models the amount or size of a growth entity. So if k is greater than 0, positive 1, positive 2, positive 3, and so on, we have a growth function. A sub 0, again, is the initial amount or size of the growing entity at time t equals 0. So when the project begins, if you're studying growth of bacteria, if you're studying or looking to see how much your investments are growing, t equals 0 is when you begin. A is the amount at specific time t, and k is a constant representing the growth rate. So what I'd like to point out to you here is that this function is very similar, if not the same, as a model that you're already accustomed to using. Remember y equals p times e to the RT power. Remember, this was the function that we used for continuously compounded interest. P represents the initial amount of investment. E was our base, raised to the rate times time in years. These are the exact same functions. We are just using slightly different variables because we're discussing different types of activities. So if k is greater than 0, we have a growth entity. But if k is less than 0, then k is negative, we would have a decaying entity. A sub 0 is still the original amount or size of the decaying entity. A is still the amount at time t, and k is our constant decay rate.